My name is René Williams. I'm an assistant professor at the Molecular Photonics group at the University of Amsterdam. And today we will discuss photoinduced energy transfer. We will talk about the Förster mechanism, which is Coulomb based, dominated by an overlap integral, and also contains the orientation factor, the kappa. We will also talk about the Dexter mechanism. The Dexter mechanism is like double electron exchange and is governed by the orbital overlap of the electronic wave functions. So we will talk about photoinduced energy transfer. So we can call the excited state, we can also call it an exciton. So we can talk about excitation energy transfer or even exciton transport. These are the terms that you can come across in this work.
In our macroscopic world, the transport of humans, food, and products is very important for our survival and economic development. Active cellular transport occurs in all living matter along filament-based highways. At the molecular level, we can transport molecules, ions, protons, electrons, and excitons. A trivial way of transport of an excited state is absorption, followed by emission, and then reabsorption of a photon. This is what we can call a radiative mechanism, and although it can be applied and is very interesting in itself, this is not what we will discuss today. There are two theoretical frameworks that we can use to describe non-radiative energy transfer processes. We have the Förster Resonance Energy Transfer mechanism, which is basically Coulomb based. It's a Coulomb interaction. And we have the Dexter energy transfer, and that is also called the exchange mechanism. Then basically it is a double electron transfer. So Förster Resonance Energy Transfer, we call it sometimes FRET. Sometimes people also say fluorescence resonance energy transfer, but it's actually not correct. So it is a Coulomb mechanism, and within this mechanism, it's especially the spectral overlap that governs the rate. So it's the overlap of the emission of the donor and the absorption of the acceptor. There's also the kappa factor, which is actually the orientation of the two transition dipole moments of the two chromophores that are involved in the process. Now, the Förster energy transfer is mainly important for singlet energy transfer. The Dexter energy transfer mechanism, it can be viewed as a double electron transfer. So it's the exchange mechanism. So because it is governed by electron transfer, the electronic coupling is what is the major important factor. So it is the orbital overlap of the donor and acceptor orbitals. Now the Dexter mechanism is mainly important for a triplet energy transfer. However, at short distance, it can actually be faster than the Förster mechanism, so then it can also be important. If we are able to make arrays of ordered chromophoric units that also contain an energetic alignment, we can use them for light harvesting and to activate redox reactions, like nature does. Photoinduced energy transfer is also applied in security features in banknotes.
Okay, so here we see an array of light absorbers that we can apply when we want to harvest light. So we see here in blue, we see the scorane, just this funny molecule with this square in the middle. Next to it, we have the bacterial chlorophyll. Then in orange, we see the phthalocyanin. Next to it, the naphthalene, the pyrroline bis imide. So that's the pink one here. So these are some chromophores that are usually applied to harvest light and to maybe apply in energy transfer. And at the other side, we have in green, now we first have the iridium compound. So iridium complexes, they actually don't absorb a lot of light, only in the UV. Next to it, we have in green, ruthenium trisbipi. So that's the green one with the typical absorption at 450. And then in red, the naphthalene diimide. So that's this one here. So these are typical chromophores that people use for light harvesting purposes because they have nice properties. They are stable. And of course, here in black, you see the solar spectrum. So if you want to harvest as much light as possible from the solar spectrum, then you can try to make an array of these types of molecules. So here we see the structures more clearly. So the squarane, bacterial chlorophyll, phthalocyanin, the pyrroline imides, and the other ones. So these are light absorbers from a paper from René, a review. So if we want to apply energy transfer, we have two mechanisms, the Förster and the Dexter. So the Förster mechanism is a Coulombic interaction. So it's not emission of a photon and reabsorption, but it's like two transition dipole moments that couple. It's a coupled transition, a Coulombic interaction. So as the one excited state goes down, the other excited state goes up. And spectral overlap is very important here. The Dexter mechanism is like a double electron transfer. So this blue electron here goes to the other side. And at the lower levels, at the HOMO levels, this electron goes to the donor. So because it is a double electron transfer, it's an electron exchange mechanism, and it is the electronic coupling and the orbital overlap, which are the important factors. Here we see them all together. So this is singlet-singlet Förster energy transfer. As this electron goes down, that one goes up. We started with the singlet excited state on this side, and we end up with the singlet excited state on the acceptor. That is the Förster mechanism. The Dexter mechanism, we can apply it also for singlets. So then this blue electron is transferred to this level, and this green electron is transferred to the other level of the donor. So we start with a singlet excited state. We have double electron transfer, and we end up with a singlet excited state on the acceptor. So that's the singlet-singlet Dexter mechanism. We can also apply the Dexter mechanism to the triplets. So here we start with a triplet excited state. We have the transfer of the electrons, and we end up with a triplet excited state on the acceptor. So this triplet energy transfer through a Dexter mechanism. So this is how we can visualize it. What about triplet Förster energy transfer? Well, it is very unlikely to happen. Basically, it cannot happen, especially because the molar absorption coefficients of triplet states, so from the S0, from the ground state to the triplet, it is possible to sometimes observe it, but the molar absorption coefficients are maybe 1 or 2 or 5. So it is extremely weak. So in that way, it's not applicable. It's basically Förster is for singlets, but maybe there are some exceptions also mentioned in the book. So this Förster radius, that is very important in this mechanism. And basically the efficiency of the energy transfer is expressed by this equation, where R0 is this Förster distance, where the efficiency is 0.5. This RDA is the distance between donor and acceptor. So how far are they apart? You can maybe estimate it from modeling or from some other data, or just statistics. So that is the Förster radius. Now the Förster radius, you can actually calculate it from separate quantities. And this is the equation to do that. And this is for an overlap integral in nanometers. You have to be careful of the units. But basically it contains this kappa factor. So this is the kappa factor that is about the orientation of the two chromophores, the refractive index, the quantum efficiency of fluorescence of the donor, and this overlap integral. So this overlap integral, that is something that is very, very determinant. But so from these data, you can calculate this R0, this Förster distance, and so you don't even need to do the experiment for that. The overlap integral, as we said before, it is the overlap of the fluorescence of the donor and the absorption of the acceptor. So at every wavelength, you have to do like a numerical integration to get a certain number. And the larger this spectral overlap integral is, the better your Förster energy transfer is. So that is the overlap integral, a very important part of Förster mechanism. Then we have the orientation factor. So if people do not know anything about the orientation, they usually use 2/3, a kappa of 2/3, kappa square. But in many cases, you may be able to say something about the orientation of the transition dipole moments of the two chromophores and their distance. So this is, well, let's say two molecules that can interact. The transition dipole moments here are these black arrows, so you can, well, calculate them or determine them from other ways. So it is the angle between these two transition dipole moments and the line that connects the centers of the chromophores. That is the orientation factor. And so there are three angles: the angle between the two factors, the angle between the intersecting line and the one of the donor and the one of the acceptor. So this is just a coniometric relation that tells you something about the orientation of the transition dipole moments. And it is very important in Förster mechanism. So this is a more abstract way, and it also shows the limits. So the maximum value of this kappa is 4, and the minimum is 0. So if you have orthogonal transition dipole moments, then in principle, there can be no energy transfer, maybe if it's, unless there's vibrational coupling. But here we see then the intersecting line, the different angles that are displayed here. So that gives you the view of the orientation of the transition dipole moments. It is just colorimetric relations, and there are, well, two expressions that are actually equal. They give the same result, but they just use a different way of expressing the orientation. That's the kappa factor. And if people do not know anything about the orientation, then they use 2/3. This is putting everything together. So the rate is basically 1 over the lifetime of the donor, and that you can measure separately, times the R0 over R to the power of 6. So there's a certain dependence on the distance. But so the R0, you can calculate it by using this overlap integral, the quantum yield of the donor, and this kappa. So you can determine it separately. And the lifetime of the donor, you can also just determine it within a fluorescence lifetime experiment. So in that way, you can anticipate the rate. This is the same expression of the kappa again, so we have seen that. And this is a picture from one of the papers of Mr. Förster. So it's the same relation of the transition dipole moments. And well, this is the way he shows the different values that it can attain. So if you know structural information and you know the transition dipole moments, the directions, then you can apply this easily. And Okay, here we have.
Can I ask a question?
Sure, sure.
On the previous slide, it appears that the direction of the transition moment does not matter because these arrows are double-headed. Is that correct?
No, it is the angles of the transition dipole moments. It is not, their direction is not within the model, I would say, although, no, it is, it should be. So this picture is maybe not really what we want, because it does have a direction, and of course, if they are aligned, then it's maximum. Good question. Yeah, okay, I have to admit, I stole all these pictures from various people, and these kind of mistakes can be there. But here, here you see the same, that the direction of the transition dipole moment is indicated within a molecular framework. So these are two molecules that can interact, and it is the angles between the planes and the intersecting line that are playing a big role in this kappa factor.
Yeah, this slide makes more sense, I think. But is it then that if the two arrows point exactly at the same, if they are parallel, is it then larger than anti-parallel, or the other way around?
Yeah, so this here means sort of alignment of the two transition dipole moments and a maximum value. This here, and if they are parallel, pointing the same direction, the maximum is 1, and if they're orthogonal, it's like 0.
Sorry, what is anti-parallel then? Is it also 1?
Good question. It will be.
So of course you think of this as a vector, and then it has a direction, but the opposite direction is equally valid. And I think that is because the sign of the direction of the transition dipole moment depends on your definition of the axis. So something like that. So the direction is well defined of the transition dipole moment, but whether it points in this direction or that direction, it doesn't matter. So that's why you usually see double-headed arrows for transition dipole moment.
So mathematically, it would be like always be the same, no matter if it's cosine of pi or 0, right?
Yeah.
Okay. So here we have the efficiency versus distance. So this is the distance in nanometers for a particular practical combination. So you see that the efficiency stays quite high at about 5 nanometer. For this case, it drops to 50%, and then it drops off more. So this is this Förster radius. So this pair of chromophores can show an interaction up to a 5 nanometer distance, which is quite large. This is a picture from the book of Lakovic. This is a whole chapter about Förster Resonance Energy Transfer. It's a very good book, so if you want to learn more about it, this is definitely a good reference. And this other paper is just with an example, I think. I have applied the Förster relation a few times, I think 4 papers, and this is one of them with Würtner and Katharina Hippius. So in this case, we looked at these kind of Perlin image chromophores, and we looked at energy transfer, and we have determined very fast transfer times of a picosecond time scale. So it is calixarine linked Perlin bis image. And we looked at FRET processes. So this is one of the times that I have applied this method, that we have applied it. Katharina made all these kinds of difficult molecules, so a lot of synthetic work as well. And I'm not going to dwell into that. But it also shows you very nicely the way that the overlap integral actually can be determined or visualized. So here we have a particular molecule, the GRORG, so it is green, red, orange, red, green. It contains 3 different chromophores with the orange in the center. And this is the absorption spectrum of the whole system. And so here we see the absorption and emission. This is the emission of the orange chromophore, of the perylene orange. So this is the absorption and the emission of the perylene red. So you can already see that the emission of the orange chromophore and the absorption of the red chromophore, that they have a good overlap. This is the one of the green, so it's from the reference molecules. So also for the emission of the red perylene emit and the absorption of the green perylene emit, there's also a very good spectral overlap. And these compounds have very high molar absorption coefficients. They have very allowed transitions, so that also helps. Yeah, so here we see the two overlap integrals of the orange emission and the red absorption, and the red emission and the green absorption. This is a better picture. So here you see in red, there's one overlap integral, and in green, there's the other overlap integral. So from the data of the separate chromophores, you can calculate these overlap integrals, and they give you some clue whether this process really can happen and how efficient it can be. Now, in this particular case, it was especially nice because there were X-ray structures from these systems. So we knew exactly the orientation, the kappa factor. We could just determine it very exact. And this is the X-ray structure for some molecules. The other ones were done with modeling. So if you know all the angles and the distance, you can fully correlate it to the Förster theory. That's not always the case, but here it was possible. So with time resolved spectroscopy, you can just determine how fast the excited state absorption of one converts into the excited state absorption of the other. And in this case, it was 1.6 picoseconds. For the other ones, it was also performed. So it gives you some information on the kinetics, how fast do these processes go experimentally with the molecules. And okay, I'm not going to talk about the spectra, but they're just fingerprints of the excited state of the molecules, and they were determined with transient absorption spectroscopy from probe spectroscopy. And yeah, basically this is displaying the various processes. So 1.4 picosecond as the first Fred step, and 1.8 picosecond as the second Fred Förster Resonance Energy Transfer step. So this is experimentally determined rates. Now they were correlated to the Förster model. So here we see observed rates and calculated rates together with this spectral overlap integral. Yeah, so this is the per mole per centimeter nanometer to the power 4. This is the typical units of the overlap integral for the different steps. And well, you see that the correlation between the experimentally observed time and the calculated time using the Förster model, well, it's very, very good. It's excellent. So this Förster model, it is very old. He did it like in the 50s, but it is really an excellent model. You can really explain your results with it very accurately. It is really, I think the guy deserves a Nobel Prize, but well, yeah, I think he doesn't live anymore. We also applied it to these molecular squares. These you must have seen them before. So we used pyrene and the perylene imide as the acceptor, and we had energy and electron transfer. These funny squares. So here we see that this is a typical signature of the Förster Resonance Energy Transfer process. So the time resolved emission of the pyrene, as it decays, as the emission goes down faster than the pyrene by itself. The emission of the perylene imide, it has a rise time. It grows in the signal. And these times are complementary, and you can basically calculate a similar time scale with the Förster model. So the Förster Resonance Energy Transfer model, it really is, you can apply it to your systems. It works like a charm. It really gives you basically exactly the rates that you can measure. And it contains a lot of detailed information on the separate units. That's one of the nice things. So that is about Förster Resonance Energy Transfer for now. The Dexter. So
can I ask a question in between?
Sure.
I have a question about this kappa.
Yeah.
Because I think you said you can calculate this kappa if you have the X-ray structure known, but this is different than for solvent, right? So in solvent you have different angles and distances.
So if you have collisional processes, then the molecules have random orientations. But if you put them either in a solid or if you link them together by some covalent bonds, then you can control the orientation of the transition dipole moments. And that gives you extra information. So a lot of studies, they use 2/3, 2/3 for the kappa factor, because they don't know the orientation. And that is like the general accepted value if you don't have the information. But if you do have information about the orientation of the transition dipole moments, then it can fit the model better. You have more input. For an X-ray or for modeling.
So this kappa doesn't have to be exactly correct, but it is a good. It is good to use it as an estimation.
So, normally people use 2/3, so 0.67 or so. But in this case, okay, accidentally or somehow, we were able to have an X-ray of such a molecule. So we had a very good indication of this kappa factor. Actually, in the beginning, the first paper, the Jack's paper, they actually showed the molecules like this. So then they did not have an X-ray yet, and they thought they were like parallel and not like this. But the orientation, okay, it does play a role, a rather big role, but like a factor 4, and that changes the rate by a factor 4. So still, it is reasonable. It's reasonable.
Okay.
Yeah. So that is the Förster mechanism. Now we will talk about the Dexter mechanism. So that is double electron exchange, double electron transfer. And it is the electronic coupling. So it is the orbital overlap of the donor and acceptor that play a role. The expression, well, it looks a bit similar. Eh? So this is the expression for the Dexter energy transfer rate. So there's like a pre-exponential factor again, but this is the electronic coupling. This VDA is the electronic coupling between the donor and acceptor. And there is also a overlap integral, but it's normalized. So it is not determined by the molar absorption coefficients or the intensity of the emission, but it is like a scaling factor. It is not as well defined as for the Förster and not as determinant. It's more the electronic coupling, and the electronic coupling is a function of distance, and this beta factor is the distance dependence factor, so the attenuation factor of the electronic coupling. So the Dexter mechanism, it's a double electron transfer. It is not so easy to predict how good this mechanism will operate. The nice thing about the Förster mechanism is that you can take the information from the separate components and then put it together, and that gives you a reasonable estimation.
Sorry, can I ask you something?
Sure.
About the attenuation factor. What does it really mean?
Okay, we will get to that shortly, but it implies how fast the orbital overlap decreases with distance. So if you have two orbitals that can overlap in space, like two pi orbitals, how does the overlap of the orbitals change when you separate them more? And whether there is vacuum in between or a phenyl bridge or a triple bond bridge, that is the determining the beta. But we will get back to that. You can ask your question again in a few minutes.
Yes.
Hopefully it will have become better, clearer. So this is also an interesting paper about these couplings. So this is an example of Dexter energy transfer, triplet energy transfer process. So you see the ruthenium trisbipyridine. If you excite it, it forms this triplet metal to ligand charge transfer state. And this MLCT state, it can transport its energy to the triplet MLCT state of an osmium compound because it's lower in energy. And that's the Dexter mechanism. And here they have studied this process as a function of the bridge. And the bridge either contains 3, 5, or 7 phenyl groups. And that influences the lifetime of the ruthenium emission. So if we start with 3, so with 3 phenols in between, then basically all the emission comes from the osmium. So that implies that the transfer process is quite efficient. With 5 phenols in between, you still see some of the ruthenium emission. So it has become less efficient. The energy transfer process has become slower. And okay, here you see, of course, the rates. So it goes from 1.5 nanosecond transfer time to 68 to 163. And 163 is close to the lifetime of the ruthenium system itself. So for 7, you only see the emission of the MLCT state of the ruthenium, this one here. And so that then the transfer is become less efficient. So in this case, they studied the efficiency of the Dexter energy transfer, or the rate of the Dexter energy transfer, as a function of medium in between the 2 units. And yeah, if we do that, then we can actually determine this beta factor. So if you take the natural logarithm of the rate and you plot it against the distance between the 2 chromophores, then the slope of this plot gives you the beta factor. So the beta factor, it tells you how does the rate decrease if you increase the distance. So if there is in between your donor acceptor, is there vacuum does not conduct or help the transfer process at all. So the beta factor is very high. If you put in between your donor acceptor something like polyparaphenylene phenylene, this conductive polymer, then you can get very low beta values. And of course, if your beta value is 0, then your line is straight. Then your rate does not change if you increase the distance. So that tells you something about the beta factor. And it's the same type of beta factor as in electron transfer. So it shows you something about the distance dependence. How does the rate change if you change the distance? And if you can think about it, then the question is, how does this rate change? Well, just like basically the electron density of an orbital. So it changes exponentially with distance. So if you have very close by, the transfer process can be very fast. If you pull the chromophores apart, then the rate will change in an exponential way. It will decrease with an exponential factor. So that is why it is indicative of orbital overlap, because you have 2 orbitals that have to sort of meet in the middle a bit. And this is the exponential decay. This is a picture from the book. So this beta factor, the rate of energy transfer, is like a pre-exponential factor times an exponent of this beta of the energy transfer and the distance. This is for the exchange mechanism, this double electron transfer. Now, if you look at the separate processes, then this is one of the steps, step 1. It basically has a beta factor that can also be seen in electron transfer studies, where you just transfer 1 electron. But of course, you also have the other electron transfer that, in this case, they call a hole transfer. It's like what is your reference points, the hole, the position where the electron is missing or where the electron is. Basically, this is the electron transfer between the 2 HOMO levels. You can call it a hole transfer. And this beta that is applicable here is, it can be slightly different than the one from the from this one, from the electron transfer case. So the whole transfer can have a different distance dependence as compared to the LUMO-LUMO electron transfer. So the energy transfer rate is correlated to this beta, and that approaches the sum of the two processes. So it's like a factor 2 if they are identical. So that tells you something about the distance dependence of the Dexter mechanism, and that is different from the one of the Förster mechanism. And so this displays the difference, and of course it is related to a situation where the beta is not too big. So this line, this sloping line that levels off quite slowly at the end, that is the Förster mechanism. So it is, that's how the rate changes with distance. The Dexter mechanism, if you put the natural logarithm of the rate here, then it has a straight line. Now the beta actually tells you what the slope is. So if the beta is 0, then the slope, there's no slope. So if your beta is very, very small, then this line can actually go like this, that it is higher than the Förster mechanism. There's also papers where they are basically at a distance, a small distance, where the two mechanisms can operate. So you have a Förster contribution and a Dexter contribution, but that's rare, that's rare. But this is how you can think about the distance dependence of the Förster mechanism and the Dexter mechanism. So it is a different way that they correlate.
So how can you really determine whether you have a Förster or Dexter?
Well, you can, for instance, look at the distance dependence of the rate. And is there an r to the power 6, or is there just a natural logarithm of the rate? So the distance dependence, but also, so if you calculate the Förster rate by the Förster model, and it does not correlate at all with what you measure, then it may indicate that there's something else happening. Then maybe the Dexter mechanism is playing a role, and the other way around.
Okay, yeah, clear.
So these are the two guys, Mr. Dexter and Mr. Förster, a long time ago, and the two papers. So it's really, both of them is a long time ago, but there's still a lot of importance to these mechanisms. I'm almost at the end, but there's a few things that I would like to say, unless Fred has another comment. No? So this is a very interesting, yes?
We can all be very envious of very important scientists like Dexter and Förster. Förster actually made a lot of great contributions. This is really, these people made their work in their universities or institutes, and we still use that today. So this is, these people are really successful. That's just want to say that.
Exactly. Okay, so this here is a website, Photochemcat, and the website contains downloadable calculation models that you can calculate things about Förster and Dexter mechanism. It also contains a load of spectra of molecules, absorption spectra, emission spectra, and Mr. Lindsay. Mr. Lindsay is also a very good scientist. Some of my PhD students, they also use his synthetic procedures from his group, and they work, they can repeat them. So if you want to apply a Förster or Dexter mechanism, you can try to look at this calculation module to see if you can get it operative and if it works for you. There's also two papers correlated to it. I have to warn you, it's only for Windows machines, not for Apple or Mac. And this is just a text. So they have Förster and Dexter energy transfer analysis and a lot of spectra. So that is, if you want to apply these models, this is interesting to look at. I have not done it myself, but well, it would be interesting to learn from your experience. Also, as Fred just mentioned, I think especially the Förster made extremely important contributions, and that is because the FRET mechanism, it is applied in a huge amount at the moment, and then especially in biology. And so this picture sort of represents that the Förster mechanism can be used to learn about conformational changes of proteins. And so here you see that the green and the yellow dot, they're close by. So now they give efficient Förster resonance energy transfer. There's a conformational change of the protein, of the bioblob, and then the distance becomes much, much larger. So the FRET efficiency drops, and you can measure that for a protein. Same for hydrolysis of a substrate, for interaction of ligands and receptors, and even for the fusion of vesicles. So if you fuse bilipid membranes, vesicles, then also the average distance of the chromophores, it will change substantially, and you can measure that. And you can not only measure that, you can actually sell assays that do that. And you can sell them to biology people. And one of our former PhD students, he's actually working at CISBIO. And it is a company that sells assays that work with Förster's theory, with the FRET theory. And they have all kinds of ways to show interaction between proteins. And so antibody-antigen interactions on a certain system, emission that changes, and you can basically correlate it to two wavelengths. One goes up and one goes down, and that tells you about the FRET process. They also do it time resolved, or they recommend to do it time resolved. That makes it easier because of background fluorescence of your biomaterial, and they can also do it in these teeter plates, in these wells. So people are making money with the theory of Förster. And they can even do it on virus particles to keep it in a temporary fashion. So here we see that an inhibitor can take away the FRET interaction between molecules, biomolecules that associate on the virus. So it is really an application. The Förster theory is really applied in assays. Yeah, one more.
We have seen that there are two theoretical frameworks that we can apply to energy transfer. The Coulomb-based Förster mechanism and one of Dexter, applying double electron transfer. If we can attain structural and energetic alignment in photostable materials, we can use the energy transfer process. Especially the Förster resonance energy transfer has many applications in biology where it is used as a spectroscopic ruler, giving information about proximity of two different proteins.
Okay. So this is my contribution about energy transfer. If there are questions or comments, we can discuss them now or next time, what you want.
Yeah, I still have a question. I am not very comfortable with these Dexter and Förster overlap integrals. I don't really understand them. And I don't see where the Frank-Condon factor ties in there in both these mechanisms, actually. How do these mechanisms depend on the Frank-Condon factor? That's basically my question.
Yeah, so in the book, I think it is described that actually the spectral overlap integral, that is a measure for the Frank-Condon overlap. Okay, we will discuss the Frank-Condon factor in electron transfer next time in more detail. For the energy transfer processes, I have not focused on that. But we can think about it more.
Yeah, well, especially for the Dexter mechanism, I don't know. I don't really know how I should visualize it, because you have basically a double electron transfer. Should you then consider both the vibrational overlap between two LUMOs and two HOMOs, or yeah, is that the way to approach it?
It's the electronic overlap. So the electronic coupling in the electron transfer is basically similar to the electronic coupling in the Dexter mechanism. So it is the LUMO-LUMO interaction for the one transfer, and the interaction between the HOMO-HOMO for the other transfer. But it's the overlap of electronic wave functions. That is the electronic part. And for Dexter, the electronic part is more important. Does that get you any further?
Yeah, a little bit, but still the Frank-Coulomb part is a bit confusing me. Well, I don't really see how it appears in these formulas, but I think it may be related to the point you also made about the oscillator strength, that for Förster mechanism that is crucial, but not for Dexter. Although that's not directly related to the Frank-Coulomb factor, but maybe that's kind of. I will think about it more.
So I hope to present something about electron transfer somewhere next week or in the coming periods, and the Frank-Coulomb weight density of states may become a little bit more clear. And if we just discuss electron transfer, it's also more comprehensive.